All right, let's dive into something I think you'll find really interesting, especially with your background in philosophy. We're talking about intuitionistic logic. And, it's not about picking sides, classical versus intuitionistic. It's more about getting this grasp of a really different way of looking at things, a perspective that's had a huge impact, on everything from math, like the foundations of mathematics, all the way to
hmm
computer science.
Absolutely. I mean, this is a system that really gets you thinking about some fundamental assumptions about, well, about truth, about proof, about how we know things. And it all comes down to this different view of what mathematics actually is. So, yeah, fascinating stuff, especially for a philosopher, I'd say.
So let's unpack that core idea, right? Mathematics as a construction, a mental construction. This is where Brouwer, L.E.J. Brouwer comes in, right? The big name in intuitionism. And what we see from our sources is that, for Brouwer, math isn't about symbols or some kind of external truth that's out there. Math is about the mind, like actively creating mathematical objects, creating proofs.
Yeah, and it's not about language, these constructions. It's something deeper, something more fundamental.
So intuitionism really shifts our view of mathematical truth. It's not about discovering stuff that's already out there. It's about building knowledge, like actually constructing it mentally. Big epistemological implications there,
It's
right?
huge, yeah. And what Brouwer pointed to as the origin of these mental constructions, well, it was our intuition of time. He argued that if you strip away all the sensory stuff from this, the intuition of time, what's left is just this basic awareness of one thing following another with this like continuous possibility in between. He called it the empty-tuity, kind of a catchy phrase. But that's what he saw as the fundamental ground of all mathematical intuition, the discrete and the continuous sort of come together there.
So math, for Brouwer, it's about exploring what we can build from this basic intuition.
Right, from this basic awareness of distinction and the passage of time, the most basic rhythm, like now and then, that Brouwer believed, underpins all our mathematical thought.
So it's a radical thought, isn't it? Like abstract mathematics coming from our internal experience of time. And the way he thought about language and logic in relation to all this, I found that really insightful. He didn't just throw them out, but he saw them as tools, secondary tools, that helped organize this fundamental mathematical activity, which happens, pre-linguistically. And that analogy he uses, comparing formal language to a score, like a musical score that goes with a symphony, is perfect.
Right, the score describes the music, but it's not the music itself, right?
Right. So mathematical activity, this mental construction, that's the primary thing. And language, logic, these are just the ways we talk about it, ways we record it.
Exactly, and that leads to a big difference in how intuitionists view truth. For them, truth isn't about some external reality, some correspondence. It's about whether you can actually do the construction that a statement describes, the mental construction.
So axioms and rules, they're more descriptive in a way.
They describe existing constructions. They can't like conjure new ones into existence out of thin air, right? And that's where they start to break away from classical logic, like with the completeness axiom for real numbers, because we don't have a universal way to actually construct the least upper bound that axiom says must exist.
Right. Okay. And then there's this distinction Brouwer made between math itself and mathematics of the second order, what we now call metamathematics, right? This
Yeah.
study of the language of mathematics. And he was pretty critical of Hilbert for blurring these lines. It's like he was saying, look, let's be clear about what we're doing, the actual creative work versus analyzing how we talk about that work. That's a pretty fundamental distinction, philosophically speaking, right?
Yeah, it is object level versus meta level.
Yeah.
And he felt that while studying formal systems might be useful, like for showing consistency and stuff, it ultimately doesn't really get at the heart of math.
Right. So a flawed theory is flawed regardless of whether you can find a contradiction in its formalization.
Exactly. Now, there's this interesting challenge that Brouwer himself acknowledged, the idea of hypothetical judgment. It's something you see in mathematics, especially in geometry, where you might start by assuming something exists, like you want to construct a specific geometric object, so you assume it exists, and then use logic to kind of explore its properties, and that eventually leads you to the actual construction.
Mm.
So it seems like logic's leading the way there, right?
Right. Yeah. It does seem like logic might be taking the lead there.
Yeah.
So how did Brouwer address that? I mean, it seems like it could be a problem for his idea of logic being subordinate to mathematics.
Well, he argued that what we're really doing in these cases is not assuming existence in the classical sense. It's more like we start by constructing a system that meets some of the conditions. Then, using tautological reasoning, logical steps, we deduce more relationships within that system until we get a set of conditions that allows us to construct the thing we were thinking about initially. So the success of the construction, that's what justifies the initial exploration.
So it's not really relying on hypothetical existence. It's more like, a step-by-step exploration.
Yeah, within the realm of potential constructions.
Okay. And our source mentions a couple of interpretations of Brouwer's response here. One, they call it alpha, suggests that implication is basically conjunction, but with the added information that the conclusion was derived from a hypothetical construction. And the other, beta, sees implication as a transformation of conditions. You show that if you meet the conditions of the premise, you can also meet the conditions of the conclusion.
Right. And both interpretations point to this idea of a proof interpretation of implication.
Okay, so what does that mean? What's a proof interpretation?
Well, it means that for an implication, like A implies B, to be valid, you need a method, a procedure to transform a proof of A into a proof of B, or, a construction satisfying the conditions of A into a construction satisfying the conditions of B.
So the meaning of if, then. It's not just about truth values anymore. It becomes about demonstrable transformation.
Yeah, exactly. It really makes you think about logical necessity in a different way. And then there's intuitionistic negation, which gets even more into this idea of proof and construction.
Right. So what we learn about is strong negation. It's about showing that a construction is impossible. Either you see it right away, or you show that assuming it's possible leads to a contradiction, like, A implies 1 equals 2. It's very concrete, tied to our ability to do these mental acts.
Right. It's not just that something isn't true, it's that you can demonstrate it can't be true. You can show the impossibility of it. And then there's weak negation, which just means you haven't found a proof yet.
And that's not a third truth value.
No, not at all. It's just a statement about what we know or don't know at this point in time. Some early criticisms of Brouwer's logic were that it was three-valued because of this distinction. But that's not accurate.
Okay, good to clear that up.
Yeah.
And now we get to the really big difference between intuitionistic logic and classical logic. The rejection of the principle of the excluded middle. This is where things really diverge.
Right, the principle of the excluded middle, or PE. In classical logic, it says that for any proposition, either it's true or its negation is true.
Seems pretty obvious, right? But Brouwer had a problem with this. A fundamental principle that we take for granted, suddenly being questioned. So why? Why did he reject it?
Because for intuitionists, PEM being valid would mean you have a method, a universal method, that for any proposition could either give you a construction to prove it or show that such a construction is impossible.
Right, like a magic decision procedure.
Exactly, but we don't have that. Think about unsolved problems in mathematics, like, are there infinitely many twin primes? We don't have a proof, and we haven't proven that there are only finitely many.
So we can't just assume one of them must be true just because of PM.
Right, exactly. And Brouwer's examples with the decimal expansion of pi are really good illustrations of this. Like, does the digit 7 appear infinitely many times, or is there a sequence of a million threes somewhere in there? We don't have a constructive proof for either the proposition or its negation.
So they become weak counterexamples to PM. So unlike classical logic, which says everything is either true or false, intuitionism says, well, not necessarily.
Unless we can actually show it to be one or the other.
Now, Brouwer wasn't saying that PM is false, like that its negation is true. In fact, intuitionistic logic does validate the double negation of PM.
Right. It's more that blindly applying PM can lead to asserting things that don't have a constructive basis, these non-truths, as he called them. He did say that in limited contexts, like with finite domains, PM could be considered valid because, in principle, you can check every possibility.
Right, so it's okay if you can actually survey everything, but the general belief in its universal application.
That's what he saw as an unjustified extrapolation. And it's interesting, even Brouwer's own understanding of PM changed over time. He had a slightly different view before refining it around 1908.
Interesting how these ideas develop, right. Okay, so then there's this other maybe counterintuitive idea from Brouwer, the non-existence of absolutely undecidable propositions.
Right, so this seems to contradict the idea of unsolved problems, right. But his argument was that you can't definitively prove that something can never be decided. Because if you could, that would itself be a decision.
So you'd be proving the negation of decidability.
Exactly. And this ties back to the intuitionistic validity of the double negation of PM. We might not have a constructive decision for A or not A now, but we also can't prove that such a decision is impossible.
So we might not know the answer now, but we can't say we'll never know it.
Okay.
Okay, and then our source talks about the implicit proof interpretation in Brouwer's work, before Haiting made it explicit.
Right, and there are some good examples of this in his actual mathematical practice. Like in 1923, he proved that not A is equivalent to not A. And the key move there relies on the idea that if A implies B holds, then not B implies not A must also hold. But he couldn't have made that inference if he thought you always needed a proof of A to start with.
So it's about the potential to move from one proof to another, not about having a proof of the starting point already.
Exactly. And the bar theorem is another example, the way he phrases his proof. If A has been demonstrated, then B is demonstrable. It shows that it's not just about the conditions for a proof, but about actually having a demonstration of A as the starting point.
Okay, and what about the ordering axioms?
Yeah, around 1925, he talked about the axioms for virtual ordering, and he specifically said that if the premises of an axiom are met, meaning you have the constructions for them, then the virtually ordered set should give you a construction for the conclusion of the axiom. So again, very clearly the proof interpretation. Fulfilling the antecedent means you can construct the consequence.
Okay, so even before it was all laid out formally, the proof interpretation was kind of guiding his work. Now let's talk about Haiting, Brouwer's student. He really took on the task of formalizing intuitionistic logic.
Yeah, and it's interesting, the Dutch Mathematical Society actually had a contest in 1927 asking for someone to codify Brouwer's logic. That's what got Haiting started.
A logic codification contest, wow.
Yeah, and Haiting submitted a manuscript in 1928, but unfortunately it seems to be lost.
Well, that's a shame.
Yeah. But the important thing is that this was before he really formulated the proof interpretation explicitly. So he was trying to formalize the system before fully explaining the meaning of the logical connectives.
It's like writing down the rules of the game just by watching someone play it.
Right. Very good analogy. And it was not until later in his work from 1930 onwards that he really started to lay out the meaning of the connectives in an intuitionistic framework. And this is where the BHK interpretation really took shape.
BHK, that's Brouwer, Haiting, Kolmogorov, right?
Yes, exactly. So the BHK interpretation, it gives specific clauses for what constitutes a proof for each connective. For conjunction, you need proofs of both parts. For disjunction, you need a proof of one of them, and you have to say which one. For implication, you need a construction that transforms a proof of the antecedent into a proof of the consequent. Negation, you need a construction that leads to a contradiction if you assume the proposition is true. For a universal statement, you need a construction that works for any element in the domain. And for an existential statement, you need a specific element and a proof for that element. And importantly, the base clause, what's often called H0, connects atomic propositions back to Brouwer's idea. A proof of an atomic proposition is a construction that makes it true.
So truth here is really tied to our ability to construct a proof. Quite a shift from classical logic.
Absolutely. It's not about correspondence with some external reality anymore. It's about our ability to verify, to construct a justification. And as our source mentions, even though these clauses might seem simple, the terms construction, presenting, transformation, these can be interpreted in different ways, even in ways that might allow for some aspects of classical logic. But in the intuitionistic context, they're meant to be understood in a very specific way, tied to this idea of constructability. And some argue that proof explanation is a better term than proof interpretation, because it's not about formally interpreting one system in another, but about explaining what the connectives actually mean in this framework.
Right, so it's more foundational, more about the meaning itself.
Mm.
And our source talks about Haiting's own writings from 1930 and 1931, where he uses this language of knowing how to prove and relates it to phenomenology, intention, and fulfillment.
Yeah, he talks about propositions expressing expectations or intentions and fulfilling those intentions through constructions. And his 1930 letter to Freudenthal is really important. That's where he explicitly defines implication as having a construction that can derive a proof of the consequent from any proof of the antecedent.
That's the standard proof interpretation right there, solidified.
Yeah.
Okay, so then there's Kolmogorov, who came up with this logic of problems. How does that fit in?
Well, in 1932, he proposed this alternative interpretation where the focus is on problems and solutions instead of propositions and proofs. So, for example, conjunction becomes the problem of solving both problems, disjunction is solving at least one, implication is reducing the solution of one problem to the solution of another, and negation is deriving a contradiction from a hypothetical solution.
So A implies B becomes the problem of figuring out how to solve B if you know how to solve A.
Interesting. And Kolmogorov actually thought we should replace intuitionistic logic with this calculus of problems, right? Yeah, he saw problems as the primary things in mathematics, more so than propositions. But as our source points out, his view and Haiting's actually ended up converging quite a bit. They both recognize the connection between intentions and fulfillments on the one hand, and problems and solutions on the other.
Right, so two seemingly different starting points ending up in a similar place. That's cool.
Hmm.
What about ex falso quod libet, the principle that from a contradiction, anything follows? How did intuitionists deal with that?
Well, Kolmogorov justified it by saying that a proof of impossibility, meaning deriving a contradiction, basically makes the corresponding problem meaningless. And he said such a proof should be considered a solution to any problem. So it's like a higher order solution to implication when the antecedent is a contradiction. Hating initially included ex falso in his formalizations, but he had more trouble justifying it based on his ideas of intention and fulfillment. In 1934, he actually explained it in a way that was similar to Kolmogorov's approach. And then later, in 1956, he tried to justify it by saying that deducing a contradiction from a proposition can be seen as a construction leading to any other proposition.
That justification was seen as a bit strained, right?
Yeah, not entirely convincing.
Yeah.
And Brouwer, with his more descriptive view of logic, didn't really have a place for ex falso. He kind of ignored it, which I think highlights a subtle difference in how intuitionistic logic developed.
Right, so different motivations and justifications even within the same school of thought. Okay, so we've talked about Hating and Kolmogorov. Our source also mentions Glivenko and his formalizations.
Yeah, Glivenko's work in 1928 and 1929 was partly driven by the need to respond to criticisms of Brouwer's logic. People were saying it was inconsistent or three-valued, and he wanted to address that. He came up with the first rigorous axiom systems for intuitionistic propositional logic. And importantly, he showed some key connections between classical and intuitionistic logic.
Like what?
Well, he proved that if something's provable in classical logic, then its double negation is provable in intuitionistic logic. And he also showed that if the negation of something is provable classically, it's also provable intuitionistically. So these were big results for understanding the relationship between the two logics. And Kolmogorov had actually done some earlier work on double negation translation as well, so he had kind of anticipated this.
So Glivenko really helped establish intuitionistic logic as a rigorous mathematical subject. And it's interesting the way Hating went about formalizing it, starting with Principia Mathematica and then crossing out the parts that weren't intuitionistically acceptable.
Yeah.
Gives you a sense of the process.
Right, definitely. It wasn't about creating something entirely new, but about adapting existing frameworks.
Okay, now, we can't talk about intuitionistic logic without talking about Brouwer's views on the foundational debate in mathematics, the Grundlagenstreit, and his reaction to Gödel's incompleteness theorems is also fascinating.
Right. So where did Brouwer stand in the foundational debate?
Well, he was very much a mathematics-first kind of guy. He saw logic as a tool that comes from mathematical practice. And his main contribution to the debate was intuitionistic mathematics itself, which often used concepts like choice sequences that classical mathematicians didn't accept. He was initially optimistic about Hilbert's formalist program because of the consistency of certain statements, like the double negation of PEM. But ultimately, he didn't think consistency proofs were that important for actual mathematics.
What about Gödel's theorems? Those were huge, right? They changed everything. They did, yeah. But Brouwer seems to have been unfazed by the first incompleteness theorem, the one that says any sufficiently powerful system will have true but unprovable statements. He had always thought that the totality of mathematical constructions was denumerably unfinished, meaning we can always create new truths that go beyond any fixed set of axioms. There's even a story about him telling Hao Wang, the philosopher, that Gödel's first result was obvious to him. And there's a note in Carnap's diary suggesting that Brouwer's ideas might have influenced Gödel's thinking. Now, the second incompleteness theorem, the one about the impossibility of proving consistency within a system, that probably resonated more with Brouwer because it supported his skepticism about formal consistency proofs. And it's pretty amazing that later in his life, he actually had a positive view of classical logic.
Wow, really?
Yeah, he saw it as a well-defined formal system in its own right, just separate from intuitionistic mathematics.
So formal logic as a kind of elegant game, but separate from the real creative work of mathematicians. Interesting. Our source also talks about strong counterexamples and the creating subject in Brouwer's later work.
Right, so we talked about weak counterexamples, which show what we can't currently prove. Strong counterexamples are different. They try to show that applying classical principles, but interpreting them intuitionistically, leads to contradictions.
Okay, and the creating subject, that sounds like it brings the mathematician right into the logic.
It does, yeah. Starting around 1948, Brouwer used this idea of the creating subject, an idealized mathematician performing constructions, to come up with counterexamples, both weak and strong. It might seem like he's introducing a new kind of negation based on what the creating subject will never prove, but our source argues that it's actually consistent with the idea of negation as impossibility. The thought is, if the creating subject with all their power can't prove something, then it must be impossible to construct.
So it's not about subjective limitations, but objective impossibility within the framework. Okay, and lastly, we have Brouwer's classification of propositions.
Right, so he said that at any given time, a proposition can be in one of four categories. Either it's been proven true, proven false, we have an algorithm to decide it, or none of those. And he thought the third case, where we have an algorithm, could be reduced to the first two in principle.
Because if we have an algorithm, we can just run it and find out the answer.
Right, eventually. And importantly, he emphasized that propositions can move between these categories over time.
So mathematical truth is dynamic, evolving. It's fascinating stuff. Okay, so let's recap some key points. We've seen how intuitionistic logic is grounded in a constructive view of math, totally different from classical logic. We've explored the rejection of PM, the proof interpretation, and the contrasting perspectives of Brouwer, Haidt, and Kolmogorov. It really gives you a different way of thinking about truth, proof, and what it means to know something.
And as a philosopher, I think it's important to see that intuitionistic logic isn't just a mathematical curiosity. It offers a different philosophical perspective on these fundamental issues. It raises questions about the limits of formal systems, about what constitutes a valid justification, really thought-provoking stuff.
So to leave you with something to ponder, could this idea of constructability, this emphasis on actually building justifications, be applied to other areas of knowledge? Not just math, but maybe science, ethics, even metaphysics. It's a question worth exploring. And looking into how intuitionistic logic is being used today in areas like computer science and philosophy might provide some insights. Thanks for joining us on this deep dive. It's been a pleasure.